Hi everyone, I'm Julia, the chemistry tutor. Today I'm going to talk about types of chemical reactions. Okay, so there's five primary types that we're going to talk about. There's like another type underneath the type that we're going to talk about. We're going to refer to some other types of reactions, redox reactions, but I'm not going to talk heavily about those today. And I am not going to balance any of the equations that I'm doing, okay? I'm just going to talk about types of reactions, how we determine what our products are based on what our reactants are, okay? So let's get started. Okay, the first type of reaction that I'm going to talk about is a combination or synthesis reaction. Okay, so think about what those words mean. Synthesis, to make something. Okay, combination, to combine things to make something else. Okay, so if I have some chemical, we're going to call it chemical A, and it reacts with chemical B, I can combine them together to make a compound AB. Okay, so this is just some chemical A, I don't care what it is, and some chemical B. Okay, these are the reactants, and these are the products to produce. Okay, they react together to produce the products. Okay, we could also have, so in this case, this is like an element, just one type of element there, and an element makes a compound. Okay, we could also have a compound react with an element to make a compound, right? So a compound with a compound to make another compound, a different compound. Yep, I spelled all of that totally wrong. Okay. We could also have a compound react with another compound to make a different compound. Okay. So it's mostly, it's an element reacting with an element to make a compound. Okay, but it can be any combination. If you have two things on the left, two reactants, and one product on the right, that is a combination reaction. Okay, so like an example would be if I had magnesium reacting with oxygen gas and combining to make magnesium oxide. Okay, so remember from back when we did nomenclature, he's a +2 and he's a -2. So that's the correct thing, okay? The correct formula, okay? We won't worry about the fact that there's two oxygens over here and only one here. That's going to come later when I talk about balancing equations. Okay, so see how we had two elements on the right combined to make a compound on the left. Okay, we could also do, let's react that magnesium oxide with some carbon dioxide. Okay, so this is where I have a compound and a compound reacting to make a different compound. Okay, we could also do, oh, let's see. So I could do copper and let's say oxygen, right? And those could combine together to make copper oxide. Okay, so an element with an element to make a compound. I could have a compound with an element to make a compound. Okay, so the key is two or more, typically two on the left goes to one on the right. Okay, so that's our combination reaction. You combine things together to make a compound. Okay. The next type of reaction I'm going to talk about is a decomposition reaction. So think about what decomposition means. It means to break apart, right? If somebody dies, their body decomposes into its parts. Okay, so decomposition is the opposite of the combination. The decomposition, you have one thing over here breaking apart into more than one thing. Okay, it's decomposing into its parts. Okay, so it's typically you have a compound and you can get elements over here or you can get elements and compound over here. Okay, you can get a variety of different things over there. Usually in a decomposition reaction, we will tell you what the products are. Okay, sometimes it's hard to guess what the products are in a decomposition. If you're taking general chemistry, you might need to know what the products are on these. And if you need help with that, absolutely email me and I would be happy to help you out with that process. Okay. Okay, so let's do a couple of reactions for this. Okay, so let's say if I had mercury to oxide, and most decomposition reactions require heat. We use that little triangle above the arrow to say that that's heat. Okay, and that breaks apart into mercury and oxygen gas. Okay, I could have magnesium carbonate, heat it, and I can make magnesium oxide and carbon dioxide. So see how here I have a compound and I made an element and an element. Here I had a compound and I made another compound and another compound. Okay, I could have, so electrolysis, I could have water and make hydrogen and oxygen. Okay, so a compound into its element and element. Okay, I could have, this is one that a lot of you will do in laboratories, sodium bicarbonate, baking soda. Okay, and that breaks apart into sodium carbonate and carbonic acid, but this always breaks apart into water and carbon dioxide. That's an unstable acid, the carbonic acid. So it always breaks apart into water and carbon dioxide. By the way, if you've ever had carbonated water, okay, carbonated water, that is carbonic acid. Okay, and it always, as soon as you let it out into the atmosphere, release the pressure, the carbon dioxide leaves and you're left with water. Okay, so those are decomposition reactions. You have one thing on the reactants and you get two or more on the products, just the opposite of the combination reaction. Okay, one of the things I forgot to mention is you can look at combination reactions, synthesis reactions, kind of like a marriage, right? Two things are combining together into one thing, into one family, okay? We could look at decomposition reactions like a divorce, okay? They were one family and then they split apart and made like different families, different things, okay? So the next reaction we're going to talk about is single replacement reactions, okay? And there's two really important things about single replacement reactions, okay? When you have on the product side, if you have a variable charge metal, you assume a +2 charge on that metal, right? Because +2 is the most common charge for those variable charge metals, and those are the ones that they tend to form. So we don't know for sure what the charge is on the product on a variable charge metal. So we're going to assume a +2. I'll talk more about that as we do some. Okay, the other thing is you have to check the activity series to make sure the reaction occurs. So let me show you what I mean by the activity series. Okay, this is the activity series. So basically anything that's higher on the list is stronger, is more reactive. Okay, so we'll always look at our list. So we've got our activity series for metals and our activity series for nonmetals. Okay, and that'll make a lot more sense to you in just a minute. Okay, so when we are looking at these, we're looking at a single thing with a not single thing. So like an element with a compound. Oop, an element with a compound makes a different element and a different compound. Okay. So one thing comes in, kicks out the other thing, and makes a compound. And it could kick out, I could have one coming in and kicking out the other one. Oh, I did the same one there. Kicking out the other one, so A hooks up with B and kicks out C. Okay, I guess I'll write those in alphabetical order. Okay, but still it's the same thing. You have an element and a compound, makes a different element and a different compound. Okay, so single replacement. Sometimes they're called displacement reactions because one thing is coming in and displacing another thing. Okay, so these are kind of like cheaters. Okay, this guy, A, comes along. If he is stronger than B, he's going to kick his butt and take his girl, leave him by himself. Okay, same thing here. If he's stronger than this one, then he's going to kick him out, take his girl. Okay, so they're just going to come along, hanging out at the beach. One, if he's stronger, he's going to come along, take his girl. Okay, so let's look at a couple of examples of this. This is one that a lot of times in your laboratory, you will see a demonstration of this, where you take solid copper wire and you put in some silver nitrate solution. Okay, so we're looking to see if the one by itself, okay, and the metal will always kick out the metal. Okay, so we're looking to see if the copper is stronger than the silver, if he's strong enough to kick him out and take his girl. Okay, so let's pop over to this sheet. Okay, so we have copper. Oops, I need to write on that. Oh, sorry about this. Here, hold on. Okay, so we're looking at copper and silver. Okay, so we're looking at copper, the one by itself, sitting all by itself. Is he stronger than silver? Yes, he is higher than silver, so he is definitely stronger than silver. Okay, so that reaction is going to happen. So copper is going to kick out silver and hook up with the nitrate. Okay, and remember our first rule, we assume a +2 charge. So if copper is a +2 and nitrate's a -1, I need 2 nitrates for that formula to be correct. Okay, so I had an element with a compound, made a different compound, and a different element. Okay, copper was stronger than silver, so he came along, kicked him out, took his girl. Okay, so let's look at another one. So if I have zinc with, oh, and by the way, the +2, remember copper can be a +1 or a +2, but over here, copper sitting all by himself as a metal has a 0 charge. But over here, we're going to assume a +2 charge. So you don't know the charge on the variable charge metals on a product. So you have to assume that it's the +2, okay? So if I had zinc with, say, nickel chloride, and I'll make that nickel 2. Okay, so we need to see, is zinc stronger than nickel? So we go back to our little chart over here. Okay, and we find zinc and nickel. So here's nickel and here's zinc. Zinc is definitely higher than nickel, so he's stronger than nickel. So the reaction is going to happen. So zinc is going to kick nickel out, and zinc is always a +2. Okay. So I had an element with a compound, made a different compound and a different element. Okay. So what if I had aluminum with cobalt 2 nitrate? Okay, so we have to see, is aluminum stronger than cobalt? Okay, so here's my cobalt. And here's my aluminum. Okay, so aluminum is stronger than cobalt. He's higher than cobalt, so the reaction is going to happen. Okay, so aluminum is going to kick out cobalt and hook up with nitrate. Okay, and aluminum's a +3, nitrate's a -1. Okay, so I had an element with a compound and made a different compound and a different element. So if that were backwards, if I were reacting cobalt with aluminum nitrate, okay, we saw there cobalt is under aluminum. It is not stronger. This is not going to happen. We're going to say no reaction. RXN means reaction. Okay, so we're just going to say no reaction. Nothing happens. Okay, it's not going to happen. They'll just stay the same as they are. Okay, we could have, let's look at some nonmetals. So let's say I had sodium bromide with chlorine gas. Okay, so I have the compound and an element. Okay, so now I've got nonmetal, so it'll kick out the nonmetal. So that's what you're looking at here, is here we had a metal, kicks out the metal. Okay, all of these were metal, 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 metal. Okay, but now we've got nonmetal as our element, so we're looking at our nonmetal. Okay, so we pop over here looking at the nonmetals. Okay, and I have bromine is the one that's by itself, and chlorine is above it. Is that what I had? Oh, nope, I had it the other way. So chlorine is the element by itself, and it is stronger than bromine. It's higher on the list. So chlorine is going to kick out bromine, so chlorine's going to come in and take the sodium and kick bromine out by itself. Okay. If I had, let's say that I had magnesium chloride with bromine, we saw on the list that chlorine is above bromine, right? So if I'm looking at those two, bromine is lower. It is not stronger than chlorine. So we're going to say no reaction. It's not going to happen. Okay, so there's two that I want to talk about here is when we're reacting an acid. Okay, so I have an element and a compound. Okay, so this is a nonmetal and a metal, but remember, hydrogen is positive and magnesium is positive, so the magnesium would kick out the hydrogen. Okay, so that's the case when we're talking about an acid. Your metal kicks out the hydrogen. Remember, hydrogen's over there in group 1. He's like a +1 charge. So your cation, cation. Okay, so we have to look and see if magnesium is stronger than hydrogen. Okay, so we've got our magnesium is up here and hydrogen is down here. So magnesium is definitely stronger than hydrogen because he's higher on the list. So this would happen. So magnesium is going to kick out hydrogen and hook up with the chloride. Okay. So what if I reacted gold with hydrochloric acid? Okay. So is gold stronger than hydrogen? Okay. So let's see. Is gold stronger than hydrogen? Okay, so down here here's our gold and here's our hydrogen. So no, gold is definitely not stronger than hydrogen. Okay, so this is going to be a no reaction. That's not going to happen. Okay, so I want to talk about that for a second. On your periodic table, oops, copper, silver, and gold are in the same group on the periodic table. They tend to be the same. Well, those are our coinage metals, right? Those are the metals we make coins out of. Okay, so we don't want them reacting with, I don't want silver reacting with hydrochloric acid to make silver chloride and hydrogen gas because then my money would dissolve if I dropped it in vinegar or if it were sitting out in acid rain. Okay, so we don't want the coinage metals to react with acids. So there you go. Acids are not those metals are not stronger than hydrogen, so the reaction is not going to happen. Your coins are not going to dissolve. And this is also a lot of why palladium and platinum are used for a lot of things is because they don't react with acids. Okay? So, single replacement reactions. A single thing comes in and kicks out another single thing as long as it is stronger. Okay, and metals kick out metals, non-metals kick out non-metals, except for acids, metals kick out the hydrogen. Okay, so that's our single replacement or our displacement reaction. Okay, the next reaction I'm going to talk about is double replacement reactions. These are sometimes also called displacement reactions because things are displacing. Okay, so I didn't really specify that up here. These are can be called single displacement or single replacement, and these can be called double displacement or double replacement. Okay, but they're single and double. Okay, so up here, the single replacement reaction, a single thing replaced another single thing. So what do you think on a double replacement reaction? You think a double thing is going to replace another double thing? Yep, that is exactly what's going to happen. Okay, and it's when you have a compound with another compound and they're going to switch partners. Okay, so if we were looking at this in terms of like the marriage and the divorce and the cheaters, okay, these would be swingers. Okay, they just switch partners. Okay, so it's always ionic. They're ionic compounds. So I have my cation and my anion, and my cation and my anion. Okay, so my cation is going to hook up with my anion, and my cation with my anion. Okay, so remember in math, the FOIL method, outside and inside. So this is the same thing. Your outside hooks up and your inside hooks up. So A hooks up with D. Now remember, you always write your cation first. So C hooks up with B. Do not write it BC because B is an anion. Cations always get written first in the formula. Okay, so you have a compound and a compound makes a different compound and a different compound. And these are the majority of what you're going to work with when you're working with types of reactions when we get further on into chemistry. Most of the reactions are double replacement reactions, okay? So let's look at a couple of examples of this. If I had, say, silver nitrate, excuse me, with sodium chloride, okay, they're going to switch partners. So my silver hooks up with my chloride and my sodium hooks up with my nitrate. So my silver with my chloride and my sodium with my nitrate. You notice I did not write the nitrate sodium. That looks weird, right? We never write the anion first, always the cation first, okay? So they just switch partners. Okay, so what if I had magnesium sulfate with potassium hydroxide? Okay, so they're going to switch partners. So magnesium hooks up with the hydroxide and potassium hooks up with the sulfate. Okay, and these numbers here, remember, those are because of correct formulas. Potassium's a +1, sulfate's a -2. Magnesium's a +2, hydroxide's a -1. Okay, so we have to have correct formulas over there. The fact that we have more potassiums on the products than the reactants, that comes out later in balancing equations. That's the next video that I'm doing. Okay, so what if we had, say, copper 1 phosphate reacting with ammonium acetate? Okay, so that one looks crazy just because there is so much going on there. But recognize your ions, right? You've got your ammonium and your acetate. So they're going to switch partners. Copper hooks up with acetate. Ammonium hooks up with phosphate. Oop, I forgot to put my arrow in. Okay, so copper hooks up with acetate. And on this, your charge stays the same. Double replacement reactions, if whatever your variable charge is on the reactants, it's the same on the products. So over here, we know phosphate's the -3. That makes copper the +1. So copper is also +1 over here. And our acetate that he's hooking up with is -1. So that formula is correct. Now my ammonium is going to hook up with my phosphate. So ammonium with phosphate, we know ammonium is +1, phosphate -3, so I need 3 ammoniums. Okay, so it doesn't matter how much is there or what your ions are or what's going on, you just switch partners. Cation with anion, cation with anion. Double replacement reaction, they just switch partners, they're just swingers. Okay, so now I'm going to talk about a special type of double replacement reaction. Okay, and it is an acid plus a base always makes a salt and water. And for these to balance them is going to be easier to see water as HOH because water is H2O, correct? If we drew the Lewis-Dot structure, he's that guy, HOH. Okay, so we're going to say water is HOH for this process. Okay, so if I have an acid, remember acids always have hydrogens in the front. And for bases, here, I'm going to write this up here. So we have H in front. And most of our bases, okay, there are exceptions to this, which you will learn later on. But most of our bases have OHs, hydroxide, in the back. Okay, and that's how they make water, right? Because an H will hook up with an OH. Okay, so say I have sodium hydroxide. Okay, this is a double replacement reaction. My cation hooks up with my anion and my cation with my anion. Okay, so I have, I typically write the salt first. Plus HOH. Okay, so something I want you to keep in mind. This is table salt. Salt is an ionic compound. Any ionic compound is a salt. So when I say an acid plus a base makes salt plus water, I do not mean it always makes sodium chloride plus water. It only makes sodium chloride when you're reacting hydrochloric acid and sodium hydroxide. Okay, if I were to react, let's say I were reacting acetic acid with ammonium hydroxide. Okay, so my cation, my hydrogen, hooks up with my hydroxide and my ammonium with my acetate. So my ammonium hooks up with my acetate. He's +1 and -1. And my H hooks up with my OH. Okay, so we're always, and this is an ionic compound, so that is a salt. You don't know what that salt is. We never really talk about that salt. Okay, but what if I had, let's see, let's go with, well, that acid's not a very stable acid, so I'm not going to use it. So what if I had phosphoric acid with magnesium hydroxide? Okay. So my H hooks up with my OH and my magnesium hooks up with my phosphate. So magnesium with phosphate, magnesium's a +2, phosphate's a -3. So I need 3 magnesiums and 2 phosphates, and I get water. Okay, so this is also called a neutralization reaction. I don't think I'm spelling that right. Okay, because it neutralizes, right? Because if I had hydrochloric acid and I drank that, I would probably die, depending on the concentration. Okay, if I had sodium hydroxide and I drank that, I would probably die. Okay, but if you mix those two together in the perfect ratio, a 1-to-1 ratio. You have now made salt water, sodium chloride water, and you could absolutely drink that. Okay? So it's a neutralization. It neutralizes the dangers of the acid and the base. Okay? But it is a double replacement reaction. It's just a special kind of a double replacement reaction. Okay? So just to recap so far, we've got our marriage, the combination, two things combining into one. We've got the divorce, the decomposition, the one thing breaking apart into more than one thing. The single replacement reaction, the cheaters, where one comes in and if he's stronger, he kicks out the other one and takes his girl. And we've got the double replacement reaction, the swingers, that they just switch partners. Okay, so not so bad, and you can tell what they are because here I have two things on the reactants. I'm going to have one thing on the product. Here I have one thing on the reactant. I'm going to have two or more things on the product. Here I have a single thing and a double thing. That is a single replacement reaction. Because you can't switch two of them, we can't switch both of them because there isn't two to switch here. Okay, and then our double replacement reaction where they double switch, they just switch partners. Okay, so it's really easy to tell from the reactants you're given what your products are going to be, and you're going to have to do that. Okay, now I'm going to look at combustion reactions. That's our last type of reaction, like our primary types of reactions. I told you there's 5. Combination, decomposition, single replacement, double replacement, and combustion. Okay, and a combustion reaction is always you have carbons, some number of carbons over here. I'm just going to put an X for my number. Some number of hydrogens over here. I'm going to put a Y for my number. And sometimes oxygens. Okay, and I'm going to put a Z for that number. Sometimes there's oxygens in the compound, sometimes there is not. But it's always carbons and hydrogens. These are called hydrocarbons. Okay, so a hydrocarbon, if we react it with oxygen gas, and we do have to put some kind of energy into this, a spark, a fire, some kind of energy, right? Because combustion, think about combustion. If you spontaneously combust, you catch on fire. Okay, a combustion engine produces energy. It's kind of like fire. You get it doesn't actually create the fire, but it creates the energy. Okay, so combustion reactions always need some kind of a spark to get them going. And they always, always, always produce carbon dioxide and water every single time. Okay. So if your products are only carbon dioxide and water, you know it is a combustion reaction. If your reactants are only a hydrocarbon with oxygen, it's a combustion reaction. Okay. All right, so let's do a couple of these. So there's a couple of special things we're going to need to do with combustion reactions. Okay, so if I had C3H8, and by the way, that is propane. So like your propane tank on your grill at home, that is propane. If we have the oxygen gas in the air, and we set a spark to that, we get a fire, and it combusts and makes carbon dioxide and water. Okay. So the way we balance these is you always balance diatomics last. Okay. And there's a reason for that. Okay. So we're just going to do this in the, oh, we're not balancing. I'm sorry. I'm not balancing equations, so we're not even going to talk about that. I forgot. Okay. But it doesn't matter what we're talking about here. If I have, oh, by the way, and this also produces energy, right? Typically there's energy over here. And we'll call that usually kilojoules. That's the unit that we use for energy a lot of times, is either kilojoules or calories. Okay, it produces some kind of energy. So your propane burns, produces the energy that you cook your food with. Okay. So because I am not balancing these equations today, I'm really not going to talk about that whole diatomic last and all of that. We're going to do that another time. But like if I had C3H6O, this one has an oxygen in there. It doesn't matter. It is still going to make carbon dioxide, water, and energy. We don't typically put the energy into the equation. Later on, you will when you talk about equilibrium and whether it's an endothermic or exothermic reactions and those kinds of things, we'll put the energy into the equation. But for right now, if all you have on the reactants is carbons, hydrogens, oxygens, then your products are always going to be the carbon dioxide and water, and that is a combustion reaction. Okay, so one more quick thing I want to talk about. I said I would mention, oh, by the way, the combustion reactions are kind of like a free-for-all. There's all kinds of stuff going on there, right? Like it's just a free-for-all. Okay, so a free-for-all. Okay, so the one thing I do want to talk about is you guys are eventually going to talk about redox reactions. Okay. And a redox reaction is when electrons are exchanged. Okay. And that's like, don't worry about when we're talking about the ions. When the ions gain and lose electrons, those are redox reactions happening. Okay. So something just to keep in mind is a combination reaction is almost always, it is usually a redox. Okay. Reduction, oxidation. Okay, so they are usually, not always, but usually, okay? The way that you know it's a redox is if you have an element on one side and it is not an element on the other side. That's how you absolutely know it's a redox. Okay, decomposition reactions are sometimes redox. Okay. Single replacement reactions are always redox reactions because single replacement reactions always have one that is an element on one side and it's not elemental on the other side. That's ionic, okay? So those are always redox. Okay? Your double replacement reactions are never redox, okay? Unless you have a decomposition coming in at the same time as it. Okay, if there's a decomposition that happens, I talked about that earlier, where your carbonic acid is an unstable acid and always breaks apart right here. So that's a decomp. And your charges change on that one. Oh, no, they don't. Never mind. Okay, and then combustion reactions are always redox. Okay, because you always have elemental oxygen over here and it's not elemental over here. So always. Okay, so single replacements and combustion. By the way, you notice I didn't abbreviate that COMB because that could also mean combination, right? So we write it all the way out. So combustion, those are always redox. Your double replacement is never redox. And your combination and decompositions are sometimes, sometimes not. Okay. And redox reactions will be talked about later on. Okay, so that is our main types of reactions that you're going to work with in chemistry. Next, I'm going to be making a video on balancing these equations. These are called chemical equations, where you have a reactants making products. So yeah, I believe that is all I have to say about that today. Have a great day.